And then we also saw that in a PID, irreducibles are prime. That means there is no distinction between prime and irreducible elements in a principal ideal domain. Then we defined what a Euclidean domain was and gave some examples. So the primary examples are of course Z and Kx. These are our first examples, but little more interesting examples are Z adjoint I and Z adjoint omega. So these are all examples of Euclidean domains, and Euclidean domain is a principal ideal domain. So we have lots of examples therefore of PIDs. Then at the end, I defined maximal ideals in any ring, and we characterize them as if and only if the quotient is a field. And we also did a few other things with maximal ideals. So we said that they always exist. And this was an application of Zorn's lemma. Today we'll do one more application of Zorn's lemma. Maximal ideals always exist in a commutative ring which is not zero. And we saw that every ideal is contained in a maximal ideal. Not the whole ring, of course. Every ideal is contained in some maximal ideal. This is about all we did last time. Okay, so let me continue from there. So I want to continue by first looking at maximal ideals. Little more about maximal ideals. So whenever you have a concept, you need examples. So we need to see lots of examples of maximal ideals. So for example, so the simplest example, so in a field. So these fields are the simplest examples of rings. As far as commutative algebra is concerned, the simplest rings are fields. So in a field K, the zero ideal is a maximal ideal. There are only two ideals in a field, right? The zero ideal and the whole field K. That's the ideal generated by any non-zero element. And zero is a maximal ideal. The quotient of K by zero is a field, is itself, right? So in a field, zero is a maximal ideal. In Z, Pz is a maximal ideal for any prime P. And this is because if you take any, so what does it mean to be a maximal ideal? It means that you cannot find any ideal of Z which contains it properly other than whole Z. And of course you can't, because if Pz is strictly contained in some other dz, then d should divide P. So d has to be either equal to P or 1. That means either the whole of Z or Pz itself. That's exactly the definition of a maximal ideal. So this can be generalized more generally. In any PID, in any principal ideal domain, the maximal ideals are exactly the ideals generated by a single element R, where R is irreducible. Now I have to be a little bit careful in making this statement, because you could ask, okay, so first, is a field K a PID? So if I take a field, is it a principal ideal domain? Is every ideal there singly generated? And of course, the answer is yes, because it has only two ideals, 0 and the whole field. The whole field is generated by 1, say, and 0 ideal is generated by 0. So field is a PID. But there are no irreducible elements in a field, because every element of a field is either 0 or a unit. for an irreducible element, you must first have a non-zero non-unit, even to define an irreducible element. So when I say more generally, in a PID, the maximal ideals are these. In a PID, not a field. Usually, when we think about PIDs, we mean not a field, right? Fields are also PIDs, but usually when we talk about PIDs, we mean PID which is not a field. So in any PID, the maximal ideals are exactly the ideals R, where R is irreducible. So this is a simple exercise. Okay. Okay. So so this much for maximal ideals in a PID. What about when the ring is not a PID? Then what are the maximal ideals? So that's a more interesting question. So another example is, so in KXY, this is a ring, right? And this is not a PID. The ideal generated by X and Y is not a principal ideal. It's an ideal which is generated by two elements, but no single element can have both X and Y in it and not be the whole ring, right? So this is not a PID. In KXY, the ideal M, which is generated by X and Y, is a maximal ideal. So there are many ways of seeing this. So let's just understand why this ideal generated by X and Y is a maximal ideal. So one way of saying what a maximal ideal is if the quotient is a field. So if we can show that quotient of KXY by M is a field, then we will be done by showing that M is a maximal ideal. So let's call this ring R. So if R is KXY, I want to say M, the ideal generated by XY, is maximum. So one way is to show that R mod M is a field. And what field is it? One can show that R mod M is just isomorphic to K. So we'll show R mod M is isomorphic to K. Whenever you want to show that a quotient of some two things is isomorphic to a third, usual way of doing it is to use the first isomorphism theorem. We'll get a surjective map from R to K whose kernel is M. And then that will show that R mod M will be isomorphic to K. So define a surjective ring homomorphism and onto ring homomorphism from R to K, i.e. KXY to K, by, so this is, I'm calling this phi. Phi goes from KXY to K, and I'm trying to define what phi is. So I have to tell you what phi of any polynomial is. So anything in KXY is a polynomial in two variables with coefficients in K. I have to tell you what phi of XY is. Just define it to be f of 0, 0, i.e. the constant term of that polynomial. So take every polynomial to its constant term. And this is easy to check that this is an onto ring homomorphism. So check phi is onto ring hom. And now let us try to see what the kernel of phi is. Hence, because it's an onto homomorphism, R mod per phi is isomorphic to K, the image of phi. Image of phi is K because it's onto. So R mod ker phi would be K. So I claim that ker phi equals M. The kernel of phi is M, which is the ideal generated by X and Y. I want to claim this. So again, to show that two sets, so we are trying to show that this set and this set, this ideal generated by X and Y, these are the same thing. To show that two sets are the same, we have to show each one is contained in the other. So say fxy belongs to ker phi. I want to show that it belongs to the ideal generated by X and Y. That means I want to show that it is X times some polynomial plus Y times some other polynomial. So fxy is in ker phi. What does this mean? This means that f of 0, 0 is 0. Because f of xy is f of 0, 0. Phi of f of xy is f of 0, 0. So to say it belongs to ker phi means f of 0, 0 is 0. So write f of xy equals a00 plus a10x plus a01y plus a20x squared plus a11xy plus a02y squared plus so on and so forth. So write it as a polynomial in x and y, right? All these coefficients aij belong to k. That is what a general polynomial in x and y looks like. Let me just make this correction. So write f of xy is this. Then f of 0, 0. If you put x and y to be 0, all these terms will become 0. So what will be left is only a00. That's the constant term of f. So if f xy is in curve phi, then a00 is 0, which means f of xy equals a10x plus a01y plus a20x squared plus a11xy plus a02y squared plus so on and so forth. Some finite sum, right? But notice that every term in this belongs to the ideal generated by x and y. So note each term aij, xi, yj, where I plus j is greater than or equal to 1. It's not a00, it's everything else, right? Is in the ideal generated by x and y. Because either the x exponent will be positive or the y exponent will be positive. Since the sum of their exponents is greater than or equal to 1, at least one of them has to be positive. And then it will belong, if the x exponent is positive, then it will belong to the ideal generated by x, which means, of course, it's in the ideal generated by xy. Similarly, if the y exponent is positive. So every term is in this ideal, and which implies that f of xy also is in this ideal. So we have shown that curve phi is contained in the ideal generated by x and y. Conversely, if fxy belongs to this ideal, what does it mean to say it belongs to a certain ideal? It means that it can be expressed as a combination of x and y with polynomial coefficients. That means f of xy equals x times some a of xy plus y times b of xy for some a and b belonging to that ring. And what do we want to show? We want to show it is in curve phi. So we want to show that f of xy is in curve phi. That means when you set x and y to be 0, you want to get 0. I.e., want to show that f of 0, 0 is 0. But f of 0, 0, if you just calculate, is 0 times a of 0, 0 plus 0 times b of 0, 0. And that's of course equal to 0. So this shows that xy is in curve. And we have finished. So we have proved that it's the ideal generated by xy is the kernel of some ring homomorphism from R to K. So the kernel of this is M. So that means M is a maximal ideal. So this is one way. Another way is to do it directly. What does directly mean? So we want to show that xy is a maximal ideal in this ring kxy. So suppose some ideal I contains this xy properly. Then we want to show that I is the whole ring kxy. So we want to show that any ideal which contains the ideal xy strictly is the whole ring. But this is also easy. Since I contains xy strictly, there exists some f of xy in I such that f of xy is not in this ideal generated by x and y. But what does it mean to say f of xy is not in this ideal? What are all things in that ideal? The things in that ideal are exactly so. Okay, so let me put it this way. This means the constant term of f is not zero. Because if the constant term of f were zero, then as we saw, it belongs to the ideal generated by x and y. So the constant term of f of xy is non-zero. So I contains some a00 plus a10x plus a01y plus so on and so forth, where a00 is not zero. It contains some polynomial with non-zero constant term. But all the rest of the terms are also in I. But the rest of the terms are also in I, since they are in xy, since they are in the ideal generated by xy, which we have assumed is contained in I. This implies that a00 belongs to I. By subtracting the rest of them out, a00 belongs to I, but this is a non-zero element, so which implies 1 belongs to I by multiplying by the inverse. So I is the whole of kx. So we have shown that any ideal which contains it must be the whole ring. If it is strictly contains, then it's the whole ring, and that's exactly the definition of a maximal ideal. So this is another way of showing that it's a maximal ideal. So you get maximal ideals here. Now at this point, let me give you more examples of maximal ideals in this ring. So more generally, similar proof. If alpha and beta are elements of K, then the ideal generated by x minus alpha and y minus beta in kxy is a maximal ideal. The proof is very similar. And it's a very famous theorem of Hilbert that the converse is true when K is algebraically closed. So I want to state this. We are not going to be able to prove it. It involves a lot of work, but it's an important theorem, and I think you should at least know this theorem. So Hilbert's Nullstellensatz. Hilbert's Nullstellensatz states the following. So if K is an algebraically closed field, such as the complex numbers say, then the only maximal ideals in the ring kx1 up to xn are those of the form x1 minus a1, the ideal generated by x1 minus a1, x2 minus a2 up to xn minus an, where the a1 up to an all belong to K. It's very easy to show that this is a maximal ideal. That's not at all difficult. That we can do it, right? With what we know, it's very easy for us to show that the ideal generated by x1 minus a1, x2 minus a2 up to xn minus an is a maximal ideal. That's easy to show. But the Nullstellensatz is the converse. It says that these are the only maximal ideals. Every maximal ideal in that ring is of this form. And this is the first this is a very close connection between geometry and algebra. This is the first step in algebraic geometry, because what it does is, so that means, so there is a bijection between Kn, that is all n tuples of elements of K, and maximal ideals of that ring R. So studying Kn, which is geometry, right? Kn is like Rn, or vector space Rn or Cn or something like that. So studying that is the same as studying the maximal ideals of that ring. This side we have geometry, and this side we have algebra. And this Hilbert-Schultz gives you essentially an equivalence between these two. Studying the geometry points of Kn is the same as studying maximal ideals of this ring. Okay, so as I said, we cannot prove it now, but it's good to keep this in mind. So it gives you lots of examples, at least, of maximal ideals. In fact, all examples of maximal ideals in such rings. But this is not true when R is not algebraically closed. So let me give you just one more example, and then we'll go to other things. So let take the ring R, which is Rx. Polynomial ring in one variable over the field of real numbers. Then the ideal generated by x squared plus 1 is a maximal ideal. And why is it a maximal ideal? Because, as I said, in Kx, what are the maximal ideals? In any PID, the maximal ideals are generated by the irreducible elements. X squared plus 1 we know is irreducible. It doesn't have any roots in R. So this is an irreducible polynomial, and therefore it generates a maximal ideal. So this is a maximal ideal, but not of that form. Not of the form x minus alpha for alpha and alpha. This is not an ideal of that form. It doesn't contain any element of the form x minus alpha. So this is a different kind of maximal ideal. That's because R is not algebraically closed. The field of real numbers is not algebraically closed. That's why you have examples of maximal ideals which are not of that standard form given by the Schultz. Okay, so now the next thing I want to define today, I might go slightly faster than usual because I want to complete some things. So the next thing I want to define is a concept called a local ring. So as we have seen, when you have a ring, you will have maximal ideals. Typically, you will have many maximal ideals. For example, in Z, if you take any prime, it generates a maximal ideal. So there are lots of maximal ideals in Z. 2Z is a maximal ideal. 7Z is a maximal ideal. 13Z is a maximal ideal. Any prime you take, it generates a maximal ideal. So this ring has plenty of maximal ideals. A local ring, on the other hand, is a very special kind of ring. It is a ring which has a unique maximal ideal. So a ring R in which there is only one maximal ideal. We know there must be maximal ideals. All rings have maximal ideals. But if it has only one maximal ideal, such a ring is called a local ring. So let's give some examples of local rings first, and then we'll do a couple of some simple propositions. Okay. Examples of local rings. The ring in which there's only one maximal ideal, we already know one very simple example, fields. Fields are local rings. Fields have only two ideals, 0 and the whole field, and 0 is a maximal ideal. The other one is not a maximal ideal because a maximal ideal always has to be a proper ideal. So it has a unique maximal ideal, 0. Are local rings with unique maximal ideal. Being the 0 ideal. So this is one example. Now let us consider more interesting examples. So first of all, we need to look at, as I said, you cannot get examples like Z or Kx or Kxy. All of these have lots and lots of maximal ideals. So the way, if you want to get examples of local rings, you should try and look at quotients of this. So let us try and see quotients of Z. So let us answer the following question. So let R be Z mod Nz. Let us ask, for what values of n is this a local ring? Or is it at all? For what values of n, if any, is R a local ring? I want to ask this question. Okay, let me assume that n is a positive integer. We know every ideal of Z looks like this, except the zero ideal, of course, right? I'm not taking zero. I'm taking Z mod nz, where n is a positive integer. So it's a finite ring. It has only finitely many elements, 0 bar, 1 bar, up to n minus 1 bar. I'm asking, when is this a local ring? When are the ideals in this, the maximal ideals in this, only one in number, only one maximal ideal? I want to answer this question. So to answer this question, sorry?
Prime power should be a prime
Yes,
power.
exactly. When n is a prime power. So I want to just get to that. So we know that the ideals, we already know that the ideals of Z mod nz correspond to ideals of R that contain nz. So we know that ideals of Z mod nz correspond to ideals of Z that contain nz. But we know that ideals of Z which contain nz correspond exactly to the divisors of n. So for every divisor of n, say d, you will have one ideal dz which contains nz. So we want to know among these dz's, we want there to be only one maximal ideal. Further, under this correspondence, maximal ideals here will correspond to maximal ideals on the other side. Containing nz. Now, but we know what are the maximal ideals of Z. The maximal ideals of Z are the ones generated by primes. So that means we want that nz should be contained only in one prime ideal. So for R to be local, we want that nz is contained in a unique pz for p prime. So this is what we would like. But we know that nz is contained for every divisor of n, nz is always contained in dz. So n must have a unique prime divisor. That means two different primes cannot divide n. This means that n must be a prime power, i.e. n is power of a prime. So Z mod nz is a local ring exactly when n is a power of a prime. So i.e. Z mod 8z, Z mod 81z, Z mod 125z are all local rings. And what are their maximal ideals? So in the first one, it's 2z mod 8z. In the second one, it's 3z mod 81z. In the third one, it's 5z mod 125z. So these are all local rings, and these are the maximal ideals of those rings. On the other hand, while say z mod 12z, z mod 20z are not local, they have more maximal ideals. For example, in z mod 12z, so 2z mod 12z is a maximal ideal. 3z mod 12z is also a maximal ideal. And we can show that these are the only two maximal ideals in this ring, because the only prime divisors of 12 are 2 and 3. It doesn't have any more prime divisors. 6 and 4, all of these are not counted. Right? Only prime divisors are 2 and 3. So it has two maximal ideals. This ring, on the other hand, also has two maximal ideals, 2z and 5z. So rings with a finite number of maximal ideals, maybe it's not one, but if the ring has only finitely many maximal ideals, such a ring is called a semi-local ring. and I don't want to write down the definition because we are not going to really use this concept. Okay, but local rings are extremely, extremely important. Okay. Yeah. So let's do a couple of very simple characterizations of local rings. So when is a ring a local ring? So here it's a simple lemma. If the set of all non-units of R forms an ideal M, then R is a local ring and its maximal ideal is M. This is one condition for a ring to be a local ring. That is, if you take the set of all non-units of R, take all the non-units of R and put them together, suppose it's an ideal, then that forms a local ring. So for instance, in Z, right, 3 is a non-unit. -2 is a non-unit. Their sum is 1, is a unit. So the set of non-units do not form an ideal in Z. So in Z, non-units do not form an ideal because we have two non-units whose sum is a unit. So it's not a local, right? If the non-units, actually that's an if and only if condition. That it's that the lemma that I've stated one direction, which is an if and only. If and only if the set of non-units forms an ideal, then it's a local. Okay, so let's prove the lemma. So what have we given? All the non-units of R form an ideal, and that ideal we have called as M. I want to show that it's a local ring and it has only maximal ideal is M. So let I be any ideal of R. Many ways there are of saying this. It's a simple result. So let I be any ideal of R. So let any ideal of R not equal to R, not the whole ring. We know that every ideal of R is always contained in a maximal ideal. We know that I is contained in N for some maximal ideal. It may be contained in more than one maximal ideal, that's not a problem. But we know that I is contained in N for some maximal ideal. So, but always I is contained in M, I claim. Because every element of I is a non-unit. I is not the whole ring. So I is always contained in M. That means every ideal of R, which is not the whole ring, is contained in M. So any ideal of R, not the whole ring, not the whole of R, is contained in M. So you cannot have any other maximal ideal. If you have some other maximal ideal, that would also be contained in M. But if it's contained in M, it cannot be a maximal ideal. A maximal ideal can only be contained in itself and the whole ring. This means M is the only maximal ideal of R. So R is local and it has maximal ideal. The proposition says that R is a local ring and its maximal ideal is M. So that's what we have seen. M is the only maximal ideal of R, so it's local with maximal ideal. So this is one very simple observation. Another very simple observation is this. Let R be a ring and M be a maximal ideal of R, such that every element of 1 plus M is a unit. Then again, R is local with maximal ideal M. This also is easily proved. So let's just understand what it is saying. What does it mean 1 plus M? So 1 plus M, I mean, this is the definition. 1 plus M means the set of all 1 plus little m, where M is in M. So the hypothesis is I have a maximal ideal of R and every element of 1 plus M is a unit. Then I want to show that that's the only maximal ideal of R. So let's prove that. So take any x not in M. If I take an ideal not in a maximal ideal, then the ideal that it generates along with M must be the whole ring. Since M is maximal, the ideal generated by M and X is the whole ring, which means 1 can be written as some element of M plus AX for some A. So the ideal generated by M and X consists of all elements of the form M plus AX. That's easy to check, right? The ideal generated by M and X consists of every element of the form M plus AX, where M is in M and A is in R. And if that's the whole ring, then one should be, you should be able to write 1 in that form as M plus AX. So once you write this way, so 1 minus M equals AX. But 1 minus M, of course, belongs to 1 plus M. Because if M is in M, minus M is also in M. So 1 minus M belongs to 1 plus M. So AX is a unit, which means X is a unit. So what does that show? Any X which is not inside M is a unit. So any X not in M is a unit, which means all non-units are contained in M. Which means M is the set of all non-units. Because obviously, any element of M is certainly a non-unit. And on the other hand, every non-unit is contained in M, which means M is a set of all non-units. So by previous lemma, we are done. Previous lemma says if the set of all non-units forms an ideal, then R is local and that's the maximal ideal. And here we have this ideal M, which is the set of all non-units. So R must be a local ring and its unique maximal ideal must be M. Okay. Fine. So this is all I want to say about maximal ideals. Next, let's get to a generalization of maximal ideals, and these are the prime ideals. So we will do some things about prime ideals next. So an ideal P is said to be prime if P is not the whole ring, as usual, and it satisfies the following condition, and is such that if AB is in P, the product of two elements is in P, then either A should be in P or B should be in P. The product of two elements is in that ideal, then one or the other has to be in that ideal. An ideal which satisfies this condition is said to be a prime ideal. And one of the first things we did when we did maximal ideals was we showed that an ideal is maximal if and only if the quotient is a field. Similarly, we have this proposition P is prime if and only if R mod P, the quotient, is an integral domain. So recall, M is maximal if and only if R mod M is a field. So once we prove that proposition, an immediate corollary is every maximal ideal is prime. So why is it prime? If M is maximal, R mod M is a field. But a field is always an integral domain. So R mod M is an integral domain. If R mod M is an integral domain, M is prime. So every maximal ideal is prime, right? Immediate corollary. Once we prove that proposition. And the proof of that proposition is just a matter of definitions. So let's prove this. So we want to show if P is a prime ideal, then R mod P is an integral domain. We want to show that if I take two elements in R mod P, neither of which is 0, then their product is not 0. So take any two non-zero elements in R mod P. We know that a typical element of R mod P looks like some A bar, where A is in R. Say A bar and B bar. And remember that A bar means A plus B. It's just notation, right? It means the coset of A. So take two non-zero elements, A bar and B bar. That means A bar is not 0 bar and B bar is not 0 bar. We want to show that A bar B bar is not equal to 0 bar. Just convert everything into statements about R rather than in R mod P. Let's see what it says about R. A bar is not 0 means A is not in P. That's the exact thing. To say A bar is 0 means that A is in P. To say it's not 0 means it's not in P. So A is not in P and B is not in P. Which means because P is a prime ideal, AB is not in P. Since P is prime. So now take bar, which means AB bar is not 0 bar. But AB bar is A bar 0 bar. A bar B bar, sorry. So A bar B bar is not equal to 0 bar. So we have shown that if A bar is not 0 and B bar is not 0, then A bar B bar is not 0, which means that R mod P is a domain. And the other way, in fact, every step is reversible. Every step of this thing is an if and only if, so you can just go back, but let me just say it anyway. So if R mod P is a domain, assume that A, B are such that A, B belongs to P. So I want to show that P is a prime ideal. So I want to show that if AB is in P, then either A is in P or B is in P. So suppose AB is in P, this means AB bar is 0 bar, because that's what it means. For an element to be in P means its bar is 0 bar. So AB bar is 0 bar, which means A bar B bar is 0 bar. Right. But R is an integral domain. R mod P is an integral domain. So if A bar B bar is 0 bar, this implies A bar is equal to 0 bar or B bar equal to 0 bar. Since R mod P is a domain. Then back again, convert to R. This means A is in P or B is in P. And that means P is prime. So we have shown that if R mod P is a domain, then P is prime. So these two characterizations of maximal and prime ideals are important. That is, maximal if and only if the quotient is a field, and prime if and only if the quotient is an integral domain. And therefore, we immediately get lots of examples of prime ideals. So remember that prime ideals are more general, much larger class of prime ideals than maximal ideals. Because for maximal ideals, you want the quotient to be a field. For a prime ideal, you only want it to be an integral domain, which is a much lesser restriction, right? So therefore, you expect that you will find lots more examples of prime ideals than you will of maximal ideals. So first example is in any integral domain, R0 is a prime ideal. That's the definition of an integral domain. If the product of two elements is 0, then one or the other is 0. That means if the product of two elements belongs to the 0 ideal, one or the other belongs to the 0 ideal. That means the 0 ideal is a prime ideal. In Z, other than the 0 ideal, PZ is a prime ideal. For any prime P. That's because we already know PZ is a maximal ideal. The maximal ideals are always prime. Right? But Z has one ideal which is prime but not maximal, and that's this ideal. This ideal is prime, but it's not a maximal ideal because Z mod 0 is Z. That's not a field, right? So this is a prime ideal which is not a maximal ideal. And the rest are all the maximal ideals PZ. In any PID, that's a generalization. The only prime ideals are 0 and R, where R is irreducible. Any irreducible element generates a prime ideal in a PID. Now, I should mention this connection between prime ideals and prime elements. Let's not get confused between the two. Prime ideals are one thing, prime elements are something else, but there is a somewhat close connection. So, and that's, let me state that in this lemma. If R is a domain, and P in R is a prime element, then the ideal generated by P is a prime ideal. But this is very easy to prove. I'll leave it to you to prove this. Just definition. But you should not get the idea that prime ideals are always generated by one element. That's totally false, right? It's not true that prime ideals are generated by one element. We already saw that maximal ideals are prime, and in KXY, for example, the ideal generated by X and Y is a maximal ideal. So it's definitely a prime ideal, but that's not generated by one element. So it's not true that it's generated by a single element, but if it's generated by a prime element, then you do have a prime ideal. Okay. It turns out rather unexpectedly that there is a connection between nilpotent elements and prime ideals. So I want to go into this connection a little further. So there is a somewhat reasonably close connection between nilpotent elements and prime ideals in a ring. And so to prove this, to even state it, first let me observe the following. Observe that in any ring R, the set of nilpotent elements form an ideal. That is, if I have two nilpotents, the sum of two nilpotents or the difference of two nilpotents is nilpotent. And when I multiply a nilpotent by any element of the ring, I still get a nilpotent. So, proof. So, let N be the collection of all nilpotent elements of that ring R. So, we want to show that N is an ideal. So, want to show N is an ideal. So we must show that it's closed under differences and that it's closed under products of elements of R. So say A and B belong to N. So first we want to show that A minus B is also in N. What does it mean to say that they belong to N? A belongs to N implies A to the power R is 0 for some R in natural numbers. Either A is 0 or A squared is 0 or A cubed is 0 or A to the 4th is 0. Some power of A is 0. Similarly, B is nilpotent. Means some power of B is 0. What we want to show is that some power of A minus B is 0. So we want to show that A minus B to T is 0 for some T. So we want to find such a T. So to find such a T, let's just try to expand A minus B power T using the binomial theorem. The binomial theorem is a true theorem in any commutative ring with identity. It's not just the usual rings that we are familiar with. The binomial theorem is true in general. You can prove it just by induction in any commutative ring with identity. So by the binomial theorem, what is A minus B to the power T? So this is A power T plus T choose 1 A power T minus 1B. Okay, that's a minus. Plus T choose 2 A power T minus 2B squared. So on and so on. Minus 1 power T, B power T. That's what A minus B power T is. Now I want to take T so large. So suppose T is larger than or R plus S minus 1. That's the lowest that works in general, but you can take T any sufficiently large number. If T is sufficiently large, note that every term looks like each term here A power I, B power J, where I plus J is T, which we have assumed is larger than or equal to R plus S minus 1. So either I is larger than or equal to R or J is larger than or equal to S. If I is smaller than R and J is smaller than S, then I plus J will be smaller than R plus S minus 1, right? So one of them must hold. So either I is greater than or equal to R or J is greater than or equal to S, which means A power I, B power J will be 0. And which implies that A minus B to the power R plus S minus 1 is 0. So that means A minus B is also nilpotent. So a difference of nilpotents is nilpotent, or a sum similarly. And also clearly R times A is nilpotent if A is nilpotent. Same power works. So the nilpotent elements form an ideal. Now it's very important to observe that this happens only because the ring is a commutative ring where the binomial theorem holds. Binomial theorem certainly does not hold in non-commutative rings, and in non-commutative rings you can have nilpotents which the sum of which is not nilpotent. So let's first give an example. Although this course is mainly about commutative rings, it's also important to keep in mind examples of rings which are not commutative. The most important examples of those are matrix rings. So for example, in the ring R equals say Mn of C. Right? This is all n cross n matrices with complex number entries. Let's just take M2 of C. Let's not even complicate Mn. Let's just take M2 of C. So M2 of C is the set of all complex numbers, complex matrices ABCD, where ABCD are in C, with the usual addition and multiplication that you know for matrices. So the element 0, 1, 0, 0 and 0, 0, 1, 0 are both nilpotent. The square of this is square of each one is 0, but their sum, which is 0, 1, 1, 0, is a unit. Certainly not nilpotent. Unit is the worst as far as nilpotents are concerned. It's the furthest away from being nilpotent. So you can have a sum of two nilpotents to be a unit. This cannot happen in a commutative ring. In a commutative ring, the sum of nilpotents will always be nilpotent. Nilpotent elements are never units, right? Because some power is zero. So obviously they will not be units. But it's possible in non-commutative rings for sums of nilpotents to be units. Okay, that's just an aside. Don't worry about M2 of C. We will only be concerned with commutative rings. So the nilpotents form an ideal, and we make a definition. The ideal of R of all the nilpotents is called the nil radical of R. And denoted by N of R, or just N. When the ring is understood, we will just write N. N means the ideal of all nilpotents of that ring R. So again, we can try and see what are the examples. So for example, see, always when you have concepts, you have to look at examples to make sure you understand this concept. So Z mod 12Z, right? In Z mod 12Z, I already, in one previous lecture, I already identified what the nilpotents were. So the nilpotents here are just 0 bar and 6 bar, forming the ideal six Z mod 12Z, all multiples of 6. So the nil radical of this ring Z mod 12Z is, so the nil radical of Z mod 12Z is the ideal 6Z mod 12Z. So in general, you can ask, what is the nil radical of Z mod NZ? So in general, the nil radical of Z mod NZ is dz mod NZ, where D equals product of all primes that divide N. So for 12, there are only two primes which divide 12, 2 and 3, and their product is 6. That is why the nil radical was 6Z. So if you take some element, if you take something like 20, then what will be the radical? 20 is 2 squared times 5. So the nil radical will be just 1, 2 and 1, 5. So 10Z mod 20Z would be the nil radical of Z mod 20Z. So this is easy to prove, right? So this is an exercise. Okay. Yeah, one more observation I would like to make. Observe that if N is the nil radical of a ring R, then the ring R mod N has no non-zero nilpotents. 0, of course, is always nilpotent. A ring which has, okay, in general, in commutative algebra, nilpotents are a source of, you can say, problems. In the sense that rings that have nilpotents somehow are not as nice. Rings that do not have nilpotents are somewhat nice rings. So what I'm trying to say here is that if you take the nil radical of R and take the quotient R mod N, that is a nice ring that has no non-zero nilpotents. So it's a definition which we won't use, but it's good to know. So a ring with no non-zero nilpotents is called a reduced ring. Just like an integrate domain, this is another definition. A reduced ring is a ring which has no non-zero nilpotents. It can have elements which multiply to 0. It may not be an integrate domain, but it has no nilpotents. No power of an element can be 0. Right? So, for example, Z mod 30Z is a reduced ring. Why is it a reduced ring? What is the nil radical of this ring? The nil radical of this ring, you have to take all the primes which multiply to give all the primes which divide 30 and multiply them. The 3 primes which divide 30 are 2, 3 and 5. When you multiply all of them, you will get 30z. And so the nil radical of this ring is 30z mod 30z. That's just the zero ideal. So only the zero in this is nilpotent. So the ring Z mod 30z is a reduced ring. Here is another example. Not Z. Let me take kx mod x into x plus 1 is a reduced ring. It does not have any nilpotence. But if I take kx mod x squared, is not a reduced ring. The element x bar here, x bar in this ring, is not 0 because it's not divisible by x squared, but is nilpotent. Since x bar squared, which is x squared bar, is 0. Right? So x bar is a non-zero nilpotent in this ring. So it's not, this ring is not a reduced ring. Okay. So what did I want to observe? I wanted to observe that if I take the nil radical of R, then the ring R mod n has no non-zero nilpotent. So I need to prove that observation still. So proof of observation. So in R mod n, suppose x bar is nilpotent. I want to prove that if x bar is nilpotent, then x bar must be equal to 0 bar. So assume that x bar is nilpotent. What does x bar is nilpotent mean? So x bar power n is 0 bar in R mod n. What does it mean for x bar power n to be 0 bar? That means x power n belongs to the set of nilpotents. But when is an element belonging to nilpotents? That means some power of that element is 0. This means x power n power m is 0 for some m. This means x power mn is 0. This means x itself is nilpotent, which means x bar is 0 bar. So we have shown that if I take an element x bar and some power of x bar is 0, then x bar itself is 0. That means R mod n has no non-zero nilpotents, so it's a reduced ring. So you can get lots of examples of reduced rings by just taking any ring and going mod the nil radical of that ring. Okay, so coming back to the connection between primes and nilpotents, this is a proposition. And this proposition says the following. It will be somewhat surprising if you're seeing this for the first time. It will certainly be surprising. When I saw it for the first time, I certainly thought it was very interesting. Okay, the proposition says the following. So, so for any ring R, the nil radical is the intersection of all prime ideals of R. So this seems to connect two things which at first do not seem to be connected at all. So on one side you have nilpotent elements whose powers are 0. On the other side you have prime ideals which I have defined. And this thing is saying that if you intersect all the prime ideals of a ring, then you will exactly get the nil radical of such a ring. So let's prove this. So again,
all non-zero prime ideals are?
No, see, 0 may or may not be a prime. All prime ideals. If 0 is a prime ideal, you have to intersect 0 also. If 0 is a prime ideal, then you have an integral domain in which there are no non-zero nilpotents in any case. Right? You all prime ideals. I'm not saying non-zero prime ideals. Every prime ideal you have to intersect. Then you get n, I want to say. So the proof of this goes as follows. This is also an application of Zorn's lemma. That's why I want to make sure that I cover this at least. Okay, so first, I want to show two sets are equal. I have to show that each is contained in the other. So say X belongs to N. That means what? X power N is 0 for some natural number N. But 0, of course, belongs to every prime ideal, right? Which means for every prime P, X power N belongs to P, because that's 0. But if X power N belongs to P, then X also belongs to P. Since P is prime, X belongs to P. How do you do this? That's done by induction, right? Induction on N. X into X to the N minus 1 belongs to P, which means X belongs to P, or X to the N minus 1 belongs to P. If X is in P, we are done. If X to the N minus 1 belongs to P, then you proceed, which means X into X to the power N minus 2 belongs to P. So on and so forth. Formally, it's induction. You can do it by induction on N. So if you have by induction on N, if X power N belongs to a prime, then X itself belongs to prime, which means X belongs to every prime ideal. So we have shown the easy direction. The easy direction is hence N is certainly contained in the intersection of P, where P is a prime ideal of R. It's the other direction which is interesting. To show the other direction, to show other way, we will prove the contrapositive. So we will take an element X in R, which is not nilpotent, and show that it belongs to some prime ideal of P, some prime ideal of R, and it's not in some prime ideal. Make sure you understand the flow of reasoning, how this reasoning is going. We want to show that the intersection of all prime ideals is contained in the nilpotent. So you want to show that if something belongs to the intersection of every prime ideal, then it is nilpotent. That's the same thing as showing that if you take an element which is not nilpotent, then that such an element cannot be contained in every prime ideal. That means you must show that there is some prime ideal in which it is not contained. So this is done by Zorn's lemma. So we use Zorn's lemma. So what are we given? We are given an element of R which is not nilpotent. That's what you're given. So take sigma to be the collection of all ideals of R, all ideals I of R, such that X power N doesn't belong to I for any N. 1, 2, 3. Take all ideals such that X power N is never in I. How do I even know that this sigma is a non-empty set? So remember, in Zorn's lemma, there are 3 steps. You have to show it's a non-empty, partially ordered set, and every chain has an upper bound. All these 3 things you have to show. So how is sigma non-empty?
0 ideal.
And that's exactly. And that's very easy because the 0 ideal belongs to sigma. Because we know that X is not nilpotent. So no power of X is 0. That means no power of X can belong to the 0 ideal. So the 0 ideal certainly belongs to sigma. And sigma is partially ordered by inclusion, usual. Right? And we need to show that every chain has an upper bound. So to see that every chain has an upper bound, any chain in sigma has an upper bound in sigma. Let S be a chain. And then check, I leave it to you to check, that the union of all elements of S belongs to sigma and is an upper bound. For S. That's an easy check, right? So once we know this, then sigma will have a maximal element by Zorn's lemma. Sigma has a maximal element. I'll call that element P. Call it P. Now the reason I'm calling it P is because that P is necessarily a prime ideal. That's the main claim. P is a prime ideal. The first time you see it, it's a very strange construction. But this construction occurs in many contexts. This is not the only place where we use this. In lots of cases, you have a set of ideals, and a maximal element among that set of ideals will turn out to be a prime ideal. This is one such example. So we want to show that P is prime. So proof. So suppose A is not in P and B is not in P. What does it mean? If I take the ideal generated by P and A, that cannot. So the ideal generated by P and A. Okay, no, let me do this 1 second. I want to say it in the easiest way possible. So the ideal generated by P and A cannot belong to sigma, and the ideal generated by P and B does not belong to sigma. So what is sigma? Sigma is a set of ideals such that no power of X belongs, and P is a maximal element. So P, the ideal generated by P and A is strictly larger than P. So it cannot belong to sigma. If it belonged to sigma, then P would not be a maximal element. So the ideal generated by P and A and the ideal generated by P and B do not belong to sigma. This means some power of X belongs to the ideal generated by P and A. Some power of X belongs to the ideal generated by P and B. Otherwise, it would belong to sigma. If no power of X belonged to the ideal generated by P and A, it would be in sigma. This means X power M is some P1 plus Ka. X power N is some P2 plus some LB. So multiplying X power M plus N is P1 plus Ka into P2 plus LB. So this is P1 P2 plus P1 LB plus P2 Ka plus KL AB. This whole thing belongs to P. And this belongs to the ideal generated by A and B, AB. So X power M plus N can be written as a sum of an element of P and a multiple of AB. So X power M plus N belongs to PAB. This means that PAB, so I want to say this implies that AB is not in P. Otherwise, X power M plus N belongs to P, but P belongs to sigma. And so we have shown that if A is not in P and B is not in P, then AB is not in P, which means P is a prime ideal. So finally, what have we done? So finally, we have got for any non-nilpotent X, we got a prime P such that X is not in P. And that's exactly what is needed to finish the proof. Okay, so I wanted to do a little more in chapter 1 of A.T.A. McDonald. I wanted to finish most of it in this course of lectures, but I have not been able to do that. Nevertheless, I hope you will get some value out of this, and you'll be able to read at least completely the first chapter, and most importantly, to do the problems in the first chapter. That's a wonderful collection of problems, and you learn a lot by doing the problems. So that's enough for today. So I'll stop my course at this point. Thank you. Any questions?
So what about the nil radical, the Cartesian product of two rings? Can you say about in terms of nil radical of two rings?
Yes. Yeah. Yeah. That's a good question. It's we can say that. So if N1 is the nil rad of R1 and N2 is the nil rad of R2, then in R, which is R1 cross R2, the nil rad N is just N1 cross N2. And it's easy to see this because every operation is component wise. If I take an AB in R, so AB in R, nilpotent, implies AB power some N is 0. This means A power N, B power N is 0, which means A belongs to N1 and B belongs to N2. This is one direction. And the other direction, if A belongs to N1 and B belongs to N2, then some power of A is 0, some power of B is 0. The larger power, if you take, that power of AB will be 0. For other direction, if A is in N1, B is in N2, A power M is 0 and B power N is 0. If N is the max of M and N, then AB power N will be 0, which implies that AB belongs to the nil radical of R. So for a Cartesian product of rings, the nil radical is the Cartesian product of the two nil radicals. Any other questions?
So here also we state the nil radical is the intersection of prime ideals of the ring R1 plus R2.
That's correct. In any ring, the intersection of all the prime ideals will be the nil radical in any commutative ring. That's correct. Yes. See, you have to understand what are the prime. See, okay. Maybe you are asking because so you have to understand the answer to the following question. So, what are the prime ideals of R1 cross R2? The prime ideals of R1 cross R2 are of two kinds. They are either P1 cross R2 or R1 cross P2, where P1 prime ideal of R1, P2 is a prime ideal of R2. This needs proof, but not hard. I want to show that the ideals, prime ideals of R1 cross R2 are all of this kind. Two types are there. One is you take a prime ideal of R1 and cross it with R2. The other is you take a prime ideal of R2 and then take R1 cross that. These are exactly the prime ideals. And using this also, you can show that the nil radical is just N1 cross N2. This way also you can. Okay, any other questions? Okay, so if there are none, then we'll stop. Thank you. I'll try to send you the notes.
Thank you, sir. Just a minute, sir. Wait.
Yeah.
A formal thank you by Meena Madam.
So, good evening to all. On behalf of Department of Mathematics, MEPCOSLINK Engineering College, Sivakasi, I would like to thank Professor Vijay Kodiyalam, sir, IMSC Chennai, for being a part of this online workshop sponsored by CMI and NASI. I express my appreciation and gratitude for your inspiring lecture on ring theory, your experience on teaching, and your depth of knowledge and your way of presenting the topics makes our evening time most memorable, sir. The
Thank you.
subject you taught make us plan to learn more. Thank you so much for sharing your valuable time with us. We all agreed that your lecture was more interesting. We hope you can join with MEPCO again. Thank you so much, sir. Thank you.
Yeah, sure. Thank you.
Thank you,
Thank you,
sir.
sir. Thank you, sir. Thank you very much.
I'll send you the notes.
Okay, sir.